Okay, wonderful. Okay, welcome to the DDPS seminar today. Before we introduce today's speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions so that our speaker can talk without unnecessary interruption. If you have clarification questions, you are welcome to unmute yourself and ask those questions. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end of the talk today. Okay, second, no classified discussion is allowed here, so watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. Okay, that's about the logistics. Now let me introduce our speaker. It is a great honor to host today's speaker, Professor Chinesta, who is a full professor of computational physics at ENSAM, Institute of Technology in Paris, France, honorary fellow of the Institut Université de France, IUF, and fellow of the Spanish Royal Academy of Engineering. He is the president of the ESI Group Scientific Committee and the director of its scientific department. He was Airbus Group Chair Professor from 2008 to 2012, and since 2013, he is ESI Group Chair Professor on Advanced Modeling and Simulation of Materials, Structures, Processes, and Systems. He received many scientific awards in different fields: bioengineering, material forming processes, rheology, and computational mechanics, with major contributions in model order reduction and engineering artificial intelligence, both integrated in the so-called hybrid paradigm of simulation-based engineering. He received many distinctions, among them the academic palms, the French Order of Merit. In 2018, the doctorate honoris causa at the University of Zaragoza in Spain, and in 2019, the silver medal from the French CNSR. Today, Professor Chinesta will present Empowering Hybrid Twins from Physics-Informed Artificial Intelligence, which is very interesting topic. So please enjoy a wonderful talk. Now, without further ado, let me pass the baton to Professor Chinesta.
Thank you very much for your kind introduction. And I will present our most recent works that we are performing in the context of this chair with ESI Group at Arts-Métiers Institute of Technology in a lab that is part of the CNRS, that is the National Science Foundation in France. So the title, Empowering Hybrid Twins from Physics-Informed Artificial Intelligence, and my co-author, my main co-author, because there are many, is Elías Cueto from the University of Zaragoza in Spain. And in one sentence, in the last century, or the century of the arts of modeling, this means describing the reality from equations, the art of simulation, because these equations are quite complex and we need to solve this in a very efficient manner. And probably in this new millenary, in this new century, we are moving from these two arts to a new one, that is the art of decision making. And taking a decision means take the right decision at the right time, and this is not easy, and for that we need very powerful computational technologies. So I introduce the topic because in the past, engineers create designs from simulation. Now things are a little bit different because we are trying to treat the more and more complex and very complex systems, very large and very uncertain. So this is the new domain in which engineering applies. We are not only interested in defining these systems, in designing these systems, we are also interested in learning from the functioning of the systems, monitoring in order to anticipate. We are very interested in diagnosis and prognosis. And for that, nothing new, we need to compute fast and very accurate. And these two words, fast and very accurate, in the history in general, these two words are quite difficult to put together, because when we are looking for a very high accuracy, we take time in order to compute the solutions, and when we are interested in moving fast, we degrade, simplify the models, and in this case, the quality of the solution is degraded. So this means that in principle, this objective of having fast and accurate solutions is quite complex, but is needed today when we are treating, for example, a nuclear reactor or an airplane. In that case, you need to compute very, very fast, and you need to compute very accurate solutions. So this is the two key words in my presentation today, is to create this alliance between these two words, the word accurate and the word fast. And for that, I'm using this fundamental equation. This fundamental equation that writes reality, the real world around us, is equal to the things that you know, the art of modeling, the physics-based models, plus the things that you ignore, that we call the ignorance, is all the part of the reality that is not in your models. And obviously, models are models. Reality sometimes is a little bit more complex because the models is an idealization of the reality, but not the reality itself. So finally, reality is this combination, something that is coming from the physics. This is the knowledge, this is the art of modeling, and something that we ignore, something that is not in the model that we call ignorance. And in order to be very accurate, we are trying to create model based on physics. This is not new, but we need to solve them very, very fast. And for that, we are using model order reduction. That is one of the ingredients of my recipe. And when our predictions are not in agreement with the measurements, this means that there is a gap, there is a deviation, there is an ignorance. The idea is to take these deviations and create on the fly a model of that deviation. And for that, we are using only the deviation. That means only data. And we are manipulating this data by using machine learning. So finally, this equation that appears in this slide is a mix of physics, mathematics, statistics, data, and machine learning or artificial intelligence. But we need to solve all this very fast and very accurate. And this is something that we call the hybrid paradigm, the hybrid engineering, the hybrid twin. Sorry. So I will start with solving the physics very fast. This is one of the first part in this equation that I just discussed. We would like to take the model based on physics, and we would like to solve these models in real time. Why? Because we need to take decisions very, very fast, and we need to consider the existing knowledge, the existing models, but I need to solve them very, very fast in order to take very fast decisions. And for that, we are using model order reduction, and in particular, one technology that we are developing for many years that we call proper generalized decomposition. There are many others, the POD, the reduced basis, there are plenty of them. For me, there is not a question, the hour is better than the others. No, this is not the case. The hour is one possibility, and this possibility runs very well with the cases that we are treating. But there is not a question of trying to put this before the others. So what is the proper generalized decomposition? This is quite simple. In general, we are using this technique in order to circumvent the curse of dimensionality in multi-parametric models. What is a multi-parametric model? This is the first question. In this slide, you have a differential operator that is acting on the unknown field u, and u depends on space x, on time t, and it depends on a series of parameters mu1 to mu_m, and f is the loading term in this model. In order to circumvent the curse of dimensionality, our idea is to introduce all the parameters as extra coordinates. This means we are trying to solve this problem for any possible value of the parameters mu1 to mu_m, in the same way that we are trying to compute u that contains the information at each point and at each time. And for this is a nice idea, because if mu1 to mu_m are extra coordinates, as soon as I compute u, function of x, t, mu1, mu_m, I know the solution of my problem for any choice of the parameter. And this is very nice, because as soon as you have a parametric solution, we can optimize, we can simulate, we can make inverse analysis, we can propagate uncertainty, or we can make control, all them in real time, because we pre-compute the solution for any choice of the parameters. So we are very interested in computing u for any choice of the parameter, and for that reason, the parameters are not more parameters, they are extra coordinates, like the space, like the time. And finally, the problem of adding all these parameters as extra coordinate is one problem that was 3D transient, now is 3D transient and many other dimensions that are coming from the parameters. And we have obviously in that case the so-called curse of dimensionality. In order to avoid this curse of dimensionality, the idea is to use the separation of variables that establish that a function that depends on x, t, mu1, mu_m can be written or approximated by a sum from 1 to capital N of capital M functions xi, functions of x, capital N functions ti, functions of t, and after many functions pi for each one of the coordinates mu g. So finally, the separation of variables is nice, because a problem that is highly multidimensional can be written as a sum of problems that involves functions, each one of very low dimensionality. Functions x are 3D, functions t are 1D, and each of these functions pi, g are 1D, depending on the parameter in the coordinate mu g. So this is the advantage of using the separation of variables. And when you are using this separation of variables, we call it proper generalized decomposition, because it's like a proper orthogonal decomposition, but we have not orthogonality. And for this reason, we call it G, the generalized. So it's a sort of decomposition like the POD, but in this case, there are many other functions that concern the parameter, and obviously the constructor that we are using is not an orthogonal basis, and for that reason, we call it PGD, proper generalized decomposition. So in order to construct this approximation, this separated approximation of my unknown u, we are using some ingredients. The first one is we are computing a model at a time, and we call it a greedy rank 1 update. At each time, we compute one term in this sum that contains capital N terms. The second one is each time that we are computing one, obviously we have the product of unknown functions x, t, p. And in order to solve this nonlinear problem, we are using an alternated direction fixed point. And as soon as all this is defined, we put this u in this operator. We are using a standard Galerkin or Petro-Galerkin weak form, and we proceed in a standard manner in order to compute each one of these functions involved in this separated approximation. So this is beautiful, but the problem of all this is highly intrusive when you are trying to introduce this kind of representation in an existing software. And for this reason, even if we publish many papers on this technology, the intrusive PGD is very difficult to implement in the existing software. For that reason, we move to alternative approaches, and one of them is based on meta-modeling. What means meta-modeling? This is the response surfaces, and the idea is to define a parametric space. This is all the parameters in the model. These blue dots represent the choice of the parameters, the design of experiment. For each one of these points, we are running a high fidelity solution in order to obtain the solution related to each one of these choices in the parameters. We obtain a solution, a transient solution in general, that we can pre-compress in order to extract the space modes and the time modes. In this image are the blue vectors and the red vectors, and like this you can compact the high fidelity transient solutions in few vectors in space and few modes in time. And for that you can use the POD, the PGD, the cure, the aim, the cross approximation, many technologies in order to compress these very big matrices. And as soon as this is ready, and again following the rationale of the separation of variables, now that we have the modes in space and the modes in time, if each one of these solutions is related to a point in the parametric space, the only thing that we need is to add new modes in the parametric dimensions. And finally, the good news is when you perform the sum of the tensor product of the modes in space, the modes in time, and the modes in the parameter, you obtain a kind of cube. And when you have many parameters, an hypercube, in which each point represents the solution at a given point, at a given time, and for any value of the parameter. So finally, we are making a sort of regression of these solutions in the parametric space. And to make the regression, we are using advanced nonlinear regressions. That is one of the tools that are very common in machine learning. And for that, we try and we industrialize, and I present some results a little bit later, many alternatives. We know the polynomial regression. The polynomial regression, if it's linear, is too poor. And if you increase the degree and the points are not the Gauss-Lobato-Chebyshev point, you can have this kind of overfitting. Obviously, you can use orthogonal polynomials, like in the case of the so-called SSL, in which, because these points are distributed as the collocation points, you can obtain, by using an orthogonal approximation basis, very nice approximations. But the problem of that is you need a grid for the collocation points, and this explodes when you are increasing the number of dimensions. And in our case, the number of dimensions is the number of parameters, and the number of parameters is quite higher, tens, or even more. So for that reason, we decide to use sparsity. And when we are using sparsity at a double level, the first sparsity is because we are using a sparse sampling. And this is, for example, by using the hypercube Latin, the Latin hypercube. The second sparsity is because, obviously, when you are using few data and your solution is extremely nonlinear, if you are using nothing, finally your equation, your solution deviates from the reference one. In order to improve the accuracy, the idea is to use a basis that is very rich and trying to take only the right elements in order to approximate the function. And this is the sparse regularization that we can use in the elastic net, like a combination of rich and lasso, or a pure lasso regularization that we call double sparse PGD, because there is a sparse sampling and there is the sparse regularization. Obviously, this is not new. Sparse regularization has been applied many times, but the only thing that we add as something new is this sparsity is combined with the separation of variables. And this is the good news today, because we need a separation of variables in order to address highly multidimensional problems, and we are using the sparsity in order to take only the right functions in the approximation basis in order to approximate the solution, avoiding overfitting. And obviously, in order to make this, we need to combine this sparse regularization with the separation of variables. And this is our most important contribution, combining these two ingredients, separation of variables and sparse regularization. And with all this, the good news is, in order to solve a problem that contains p parameters, we are using in the order of p data, and we obtain solutions that are quite reasonable with respect to the industrial needs. And very recently, we are using exactly the same thing, but we are using a kind of quadrature that is close related to the ANOVA, the analysis of variance. And the good news here is there are also a polynomial approximation by using orthogonal polynomials. And this is also a good news, because finally, by combining everything, the separation of variables, the analysis of variance, and the sparse regularization, we obtain very, very accurate approximations by using very few data. And this is very important for us, because when we are trying to use data, the data is not so abundant, and we need to create very efficient regressions in order to adjust the models from the data. But obviously, when there are many, many dimensions, and there is low data limit, and this is the main center of interest of the techniques that we are proposing. And sometimes, again, in order to improve the accuracy, we are trying to take all the solutions that we compute offline related to different choices of the parameter, and instead of creating a regression for all the simulations, we decide to make some clustering to clusterize these solutions and to apply in each one of the clusters a regression. And as soon as all this multi-regression is ready, this means that in the future, when someone sends me the choice of the parameters, I need to identify by using a classification the cluster to which these parameters belong, and we can take the regression related to the cluster C, and I can particularize this regression for the choice of the parameters. So this is the technology based on advanced nonlinear regressions that operates in multidimensional settings at the low data limit. And in order to show you few examples, you can see here one problem that is related to the crash, extremely nonlinear. There is dynamics, there is elastoplasticity, there is damage, there is fracture. And the idea is to consider a very rich model with more than 5 million elements. There are more than 20 parameters. Each calculation takes days or weeks. And this means that we cannot perform many simulations. And the idea is, when we have about 20 parameters, we would like to compute solution with about 20 runs. And for that reason, we are using the technologies that I just introduced in order to compute the parametric solution. And now, as soon as you can change one of the parameters, you can see what is the impact in the solution. Here on the right, on the bottom, you can see a welding process. Many parameters again, the power, the velocity in the welding, etc. And as soon as this parametric solution has been computed, now you can change the parameter. You can move the parameter with these sliders, and you can observe the impact of each one of the parameters in the quantity of interest that you are representing in this solution. So finally, you spend a little bit of time in constructing this parametric solution, this response surface, but finally it's not too expensive because we are using this separation of variables combined with the sparse regularization. And with this, we have something that is quite accurate and very, very fast to compute. Here you have another example. This is an airbag, and you are trying to simulate the airbag folding. You can fold it to put in a small box that is in your car. You can unfold, and now there are many parameters, some ones related to the size of the airbag, others that are related to the geometry of the box, and you can again to fold, unfold, and this is not video games, this is the real physics. This is the membrane or shell element with contact. There are millions of contacts, so there is a phase in which we are computing the solution for different choice of the parameters, and after we are using these technologies, these regression technologies, combining the separation of variables and sparsity in order to compute these meta models. And now you can apply this in many domains, like in thermal comfort. You have your car, you have the driver, and now you can introduce many parameters. In this case, is the flow rate and the external temperature. And by moving these sliders, you can observe or you can evaluate the conditions inside. This is for thermoforming in polypropylene. And now you have here your parameters. We create by using these technologies the response surface. And now by moving this slider, you can evaluate the impact. Here you have a crash, a real one for the Yaris, in which you have the impact of different parameters that are the thicknesses of the different metallic sheets that we are using in the structure. And you can see by moving the different parameters in real time, you can evaluate the impact of these parameters in the solution. And this one is for the external aerodynamics in the turbulent flow. And here the parameters are this angle and the size of the obstacle. And finally, we are again making a sampling and a sparse sampling and computing by using the separation of variables and something related to the sparse regularization. So this is the technologies that we are using. Sometimes we need to combine with optimal transport, because you can understand that if in a problem, for one parameter you have the blue curve and for the other the orange curve, if you take a parameter that is in the middle, finally you interpolate, you will have the half of this and the half of this. And you would like to have something that is the half but located in the middle. And for that we need to combine all the regression that I just discussed, combined with the optimal transport that is a kind of an interpolation in a Lagrangian sense. And by combining all this, now you are changing the orientation in this ventilation device, and you can observe what is the velocity field of the air inside the cabin. So this is the technologies that we are using. And now the next step is, and what happens if finally we have the parameters, but the parameters are not deterministic, the parameters are stochastic. And for making this, that is, imagine this problem in which we have this specimen, these coupons. We are making a traction test, and the behavior law of these coupons follow this very well-known constitutive equation, but K, epsilon 0, and N has an stochastic distribution, so finally are not parameters we need in order to propagate uncertainty or to make robustness analysis. We need to take in consideration that this K, epsilon 0, and N are distributions and not values. So the first is sample, a design of experiments. For any choice of K, epsilon 0, and N, we have a traction curve. And the idea is, as soon as you compute your parametric solution, now the parameters are not K, epsilon 0, and N, are the average and are the standard deviation. And as soon as you compute this is the parametric solution. At the beginning, K, epsilon 0, and N are given values, and we can see that we can interpolate the solution by changing some parameter. The traction curve is moving, but the good news is a certain moment, if a certain moment we start to introduce a variance in the distribution of the parameters, we compute this kind of corridors that give you with 95% of probability that the resulting curve, traction curve, is inside, and the point at which the specimen breaks is in between this corridor that is the vertical one. So this is a way that is quite simple from a parametric solution to present the same results, but in a statistical way. This is another case, but it's not necessary that we move in. And finally, the main message is when we have components, we can use this framework, this workflow. We can compute the parametric solution, and finally, in this landing device, finally, you can compute the stresses depending on the loading, and it depends on the landing conditions. So finally, this is a very expensive calculation, but we are computing this in a parametric way by changing the different efforts that we are applying to this system. And the good news is after you can take it, because this is a response surface, and you can couple this response surface in a system engineering modeling. And this is good news because now the hydraulic or the electrical system can be combined with the high fidelity finite element simulations, and you can manipulate in real time a engineering system in which each component is high fidelity because you are using the parametric solution that you compute by using this methodology. And you arrive that a system is no more like a Lego in which you are combining the components, and each component that is parametric is dialogating with the other component. And like this, we can move from the component to the system or to the system of systems. So until now, I prove that using this kind of technologies, we can obtain quite accurate solutions of the model that we are considering. But now we have a problem. We are solving very, very fast the models that are expected describing the reality, but only expected describing. Probably the reality is much more rich, and this means that we can solve very, very fast our models, but maybe these solutions are quite far from the reality. So now we are moving to the second part. This is not only solving fast, the idea is to solving well. The idea is to obtain predictions that are very close to the reality. And for that, as you remember at the beginning, in this fundamental equation, we write that the reality is our models that now we can solve very, very fast by using all these methodologies that I just described, the model order reduction, or the meta models, or the surrogate, the thing that you want. And the idea now is, even if I can solve very fast, if my solution is not very good and there is a deviation, an important deviation with respect to the reality, I enrich my model. And in order to enrich the model, I will take the deviation, the ignorance, the gap, and I would like to use machine learning in order to online create a model of the gap. And this is very important because finally, if we can manipulate physics in real time, and I can create models of the ignorance in real time, when we put both together, I will represent the reality very well, and very fast. In order to make this, we are trying to make machine learning, and the idea is, now it's not only response surfaces. I would like to create models from this gap. And I would like that all these models that we are creating are also fulfilling the fundamental equations in mechanics. This means, for example, energy conservation, entropy production, symmetries, etc. And for making that, we start from classical analytic mechanics in which you have the axiom, you have the Lagrangian, You have the Hamiltonian, that is the Legendre transformation of the Lagrangian. And finally, you have a very nice context that obviously is only in Hamiltonian mechanics. When we are moving to irreversible thermomechanics, we need also to introduce the dissipation. And for that, in collaboration with Elias Cueto from Zaragoza, we are trying to implement the generic framework that is something in the thermodynamics of irreversible systems, in which the state of the system evolves in time from a part that is the Hamiltonian part with L, the antisymmetric matrix. This is the gradient in the phase state of the Hamiltonian, and one matrix that is symmetric and positive definite, that is semi-definite, that is the dissipation matrix, and you have the gradient in the phase space of the entropy. With some conditions, the dissipation don't affect the Hamiltonian, and the Hamiltonian don't create entropy. And with these conditions that can be written in a discrete form, you can learn models that conserve the energy and produce the entropy. And this is very important to be conservative and to be stable. And for that, the production of the entropy is a key issue. And by using these technologies, the idea is to use an state that could be very, very large. We are using an autoencoder in order to encode and to find the intrinsic dimensionality of the state of the system. After we introduce this part of thermodynamically consistent neural network, and after we have the decoder in order to come back to the standard space state. And when we are applying this, we are creating models that has all the right properties. And in this video from the team in Zaragoza, you can see we are trying to learn in a thermodynamically consistent way the movement of a fluid in a glass. Obviously, the different fluid with different rheologies, with different viscosities, the movement is not exactly the same. But we learn from this information, we apply some filters, in particular related to the TDA, the topological data analysis. We create this kind of models in order we are enforcing or we are learning a model that fulfill the thermodynamics. And now you can see the water does not exist. We are putting it inside the glass. And now we can move recipient, the container, and we can introduce virtually the fluid inside, and we can reproduce quite well the movement, the dynamics of this fluid, and everything is consistent from a thermodynamical point of view. So this is the advantage of learning in a framework that is consistent with thermodynamics. First, because the integration is stable. Second, because as soon as you introduce physics in the learning, you need much less data than if you are working or creating the model from scratch. And now the idea is we can put both together. We have the analogic world in the past, in which we have the virtual prototypes, that is the physics. We can solve physics in real time because we have model order reduction. We can introduce this in a system modeling. So this is physics in real time in a system modeling as I presented at the beginning. And this is the classical virtual twin based on physics. Now, if there is a gap between our predictions and the measurements, the idea is to take this real data, in our case is the gap, is the deviation. We would like to make data analytics in real time to create this machine learning that create these models that fulfill the thermodynamic consistency. And as soon as this model is ready, you can introduce also in the system modeling and you have a kind of digital twin of the deviation. And when you put the virtual twin, the physics, plus the model of the deviation, you obtain something that is very close to the reality. In order to illustrate it, imagine this case in the lab. We are filling this mold. This is a composite preform. This is the resin that is moving inside. There is a model, of course, there is a model. We know that the fluid is in the domain omega, that each point in the fluid domain is x. that in the fluid domain there are two variables that are very important, the pressure and the velocity. And we know from physics that the velocity is minus the permeability gradient of the pressure. This is coming from the Darcy's law that is very well known. It's a very nice approximation. And we have the fluid conservation that implies that the divergence of the velocity field is equal to 0. And when we are combining both, we obtain that the divergence of K multiplied by the gradient of pressure is equal to 0. And this is something that is implemented in many commercial software. So we take this commercial software, in our case was PAM-RTM from ESI Group, and by solving this equation for many value of the copermeability, we compute the position of the flow front depending on the parameter K. And now as soon as we compute this by using the meta-modeling that I described at the beginning, now for a large permeability, medium or a small, you can see the effects in the filling process. When the permeability is very large, the filling is very fast, and when it's very low, the permeability, the filling process is very, very slow. So finally, here there is only the post-processing because this is the parametric solution. But as I have access to the simulation in real time for any value of the permeability, now in the reality, as soon as this fluid is moving, I could try to interrogate my parametric solution in order to try to obtain the permeability that allows to predict a fluid volume, a volume of fluid that is in agreement with the experience. And from this minimization, I can obtain in real time the permeability. And you can see here in few seconds, my simulation and my experience is in perfect agreement because at the first time instance, I obtain by using an inverse technique the value of the permeability in order to make that my simulations are in agreement with the experience. So until now, this is only physics in real time, but there is not artificial intelligence. What is the problem? The problem is, imagine in this case, I calibrate very, very fast, and the physics is wonderful. My predictions are exactly the same that the experiments. So I'm very happy, but there is an ignorance that is coming because after a certain time, the experiment is absolutely different than my simulation. Why? Because in the experiment, the permeability close to the wall of the domain is very low. And finally, you can see this is the ignorance, something that exists in the reality that is not in my numerical model. And this ignorance is, in fact, the deviation that I will notice. Imagine now the hybrid paradigm. As soon as the model is enough, everything is okay. I don't need to make things. My simulation is perfect. But if at a certain moment my experiment change, my simulation adapt. Why? Because we add to the Darcy's model the model of the gap that we compute by using a regression on the difference between the prediction and the measurements. And this is the idea of the hybrid twin. We have a model. We are solving this model in real time. If everything is okay, we don't need to make things by using other technologies. But if at a certain moment my simulation does not correspond to the reality, I try to use this deviation in order to be treated by using machine learning online in order to create the model of the enrichment such that the model based on physics plus the model of the deviation represent the reality. And now, as soon as this works, we can move to the more complex cases. Only 2 slides and I finish my presentation. In this case, this is an electrical car. I create a model of the battery. I learn by using these regressions the state of charge and the voltage depending on the current that we demand to the battery. And we can introduce these models into the engineering system. And now we have the representation of the car. And now we can connect with OpenStreet or with Google Maps. And I can introduce, I would like to move from A to B. And I can predict during the time, the evolution of the state of charge or the voltage in this case. And obviously, this is the nominal, but when we start to the real itinerary, there is a deviation because in general, the things that you will experience in the reality is a little bit different to the things that you expected in your prediction. And as soon as this difference applies, the idea is to start with modeling this difference in order to keep your system always in control. And this is one of the advantages. Last example, this is coming from Dassault Aviation. In this case, they have a model, a little bit simplified, of a system in this airplane. And the question is, as this model is a little bit simplified, when we compare the prediction with the sensors, the result is not good enough. What is the idea? We use this model. This model makes predictions, and we compare the predictions with the measurements, and we make the difference. If a difference exists, this means that there is a gap, an ignorance. There is something in the system that is not in the model. And at this moment, this difference is, we create a model of this difference by using a regression, for example, a neural network or any kind of regression that I introduced at the beginning. And as soon as you create this model, you have the model of the difference. If you have the model of the difference and you have the model, the nominal model, if you put both together, you will obtain the predictions that are in perfect or almost perfect agreement with the measurements. So finally, this is the hybrid paradigm. The knowledge materialized in a physics-based model, this one, can be enriched with a data-driven model of the gap between predictions and measurements. And when you put both together in this operation, you obtain the physical reality. So now data serves in order to make diagnosis directly from the data, in order to enrich the model by using this hybrid paradigm. And when you obtain a very nice prediction of the model, you can start to make prognosis. I have no time to introduce this concept that is based on data, and I will finish with, now that we can obtain a real replica of the real physics, we consider this sentence that is quite impressive. People remember very differently what they learn after 2 weeks. 10 to 20% of what they heard or read, 90% of what they did. So this means that finally we need to touch, we need to experience the reality, even if the reality is virtual. And for that, again, Elias Cueto and his group in Zaragoza, by using all the technologies that I just described, based on physics, based on data, based on the hybridization of these tools, we create a sort of interaction with a virtual world. You have the Stanford Bunny, you have that is virtual, you have an office that is real, and we pre-compute all the interaction, all the possible interaction by using contact mechanics in hyperelastic materials. And now, as soon as this is ready, now you can start to interact with the bunny. And here we are using contact mechanics, and we are using the deformation, enlarged deformation of these hyperelastic materials. This is for the Stanford Dragon. And now you can touch virtually, obviously, because it does not exist. You can, in real time, experience the deformations. You can superpose the displacement field, the stresses, the deformations. And after, if you need to touch it from other directions, you can touch and you can appreciate, in all the cases, the very nice performances. And this is more or less the same, a recent work of Elias and the team, in which they are making something similar, but now by using, in this case, the holography. And now you can see nothing new, the Stanford Bunny, the modes, and now you are see here the bunny that appears, the holography, and now you can touch it. You can touch. obviously, at this moment, we have not the sensation of the touch is coming, but finally, you can now interact with a virtual world, and you have the real time, and you have the right deformations, because everything is coming from the equations of physics that we manipulate by using model order reduction in real time, and when needed, we can enrich by using the deviation and construct. So, main conclusion, we are trying to move forward an hybrid intelligence. We are to reach performances by design in order to augment humans. We are trying now to introduce multisensorial and emotional in this interaction between the real and the virtual world in order to empower, obviously, humanism. And all this in this new art of the decision-making for a more resilient world, in which we are trying to create an alliance between these two keywords that was accurate and fast. So in order to be accurate, the idea is to take all the knowledge, the physics, and if it's not enough, we are trying to create, by using machine learning, the model of the deviation, the gap. And when we put both together, this approximates better than reality, and this is our hybrid paradigm. So this from one side, and to proceed very, very fast, the idea is to use this model order reduction in order to compute all the possible solutions, because all the parameters are extra coordinates, and today we can create responses, we can create parametric solutions in highly multidimensional parametric spaces, even in the low data limit, by using these advanced regression technologies that we introduced just at the beginning. And this is all from my side. Thank you very much. And you have the record video, and if you need, because there are some slides that I had no time to present related to the topological data analysis, I could transfer also my PowerPoint to the organizers. Thank you very much.
Thank you so much, Professor Chinasta. There was a very nice demonstration about the digital twins and why we need a the model order reductions and machine learning for the ultimate decision-making applications. That was very nice demonstrations. I really enjoyed it. So let's have some Q&A sessions. If any, so I don't see any questions from the chat room, so please feel free to
there is one question from the chat. There is one question from the chat that is, do you assume a statistical distribution to account for the difference between the model predictions and the reality? At this moment, no. I suppose that there is a deterministic reality and a deterministic model, and finally we are creating difference. But in other cases, we consider that the model is not deterministic. As you remember at the beginning, when we treat the tensile, the traction test, we can introduce that the parameters of the model is also stochastic, and instead of having only one model, we have a corridor, and we have the model inside the corridor. And in other cases, when you have a sensor, the sensor is not giving a value, the sensor have also a variance. And in that case, when you are taking different values in the sensor, you need to consider that this is also statistic values, is stochastic. And now finally you have a kind of corridor for the data and a kind of corridor for the model. The idea is to create a model that relates the average of the model with the average of the data, and that can also model the standard deviation of each one. So this is not in my presentation, there is not, I don't consider this, but in the reality, the model is a corridor. This is an interval, because you have an average and you have a standard deviation around, and the same for the data. So when you are creating the model, we are creating a model in order to align the average behavior, and we are creating a model in order to variance.
Okay, thank you so much.
With respect
Any
to
other
the
questions
question in the chat.
Okay, awesome. Thank you. Okay, so we just got another questions from Ian. For your PGD-based emulators, the number of training sampling points are order number of parameters, correct? If you recall,
Yes.
how many sample points were used to build the 20-parameter card deformation, for example?
Yes. The idea is it depends on the technology that we use. For example, if we are using the collocation points in the SSL, imagine that you are in the lowest level. You have one in the min and one in the max. This is nice. Min and max. There are two per dimension. When you create the tensor product, if you have 10 dimensions, you need 2 power 10. So finally, it's excellent, this technology, but finally the number of points in the sampling increase exponentially with the number of dimensions. When we are using the sparse, the idea in the sparse is I put many functions in my basis, and I ask to find for the ones that in the sparsest sense can approximate the data. And for making this, as you can see in this slide, the sparse sampling, the number of runs is about or similar or very close to the number of parameters. In this case that I introduced here, that is something that we developed for Volkswagen, Gestamp, Renault, Mitsubishi, or Hyundai. If there are 20 parameters, I make only 20 runs. But 20 parameter, 20 runs does not mean that I'm making a linear regression. I'm making a strongly non-linear regression because we are regularizing by using the sparsity. So finally, we have about the same number in these applications, the same number of runs that the number of parameters, but we obtain non-linear regressions because our space of approximation is very large, and I take only the functions by using this sparse regularization. So this is separation of variables, sparse sampling, the same number of points that the number of parameters, more or less, plus the sparse regularization, sparse or rich or elastic net. So we are using kind of regularizations in order to select the right functions and avoid overfitting. This is the idea.
Okay, thank you so much. Yeah, I myself was puzzled about that too. Like I mean, I understand what you're doing, but it's hard to believe that only the 20 sample points within in the parameter space dimension was giving you a good enough accuracy as you demonstrated in the car, the Hyundai car example.
Yeah.
I definitely need to look more into that.
Yes. There is no miracle. The idea is if the solution that approximates the reality is in my approximation basis and I'm using an sparse regularization, obviously the interest is to take the function that could, with only one function, represent all the data. This is the good idea in sparse regularization. If you take an infinity of functions, imagine all the functions you introduce in your approximation function, it's sure that when you take 10 points, these 10 points are all them on the solution that exists in my basis. So the idea is there is one that is able to represent all the data. If I introduce a sparse regularization and I take exactly this function, with only one function I can represent all the data. Obviously, we have not an infinity of functions in my basis, and obviously with the sparse regularization are not finding exactly the best one. So finally it's not so optimal, but the idea is this one. The idea is if my basis is very rich, the solution is inside, and if we are something that is able to take it with only one function, I can represent my solution. So for this reason, we are using not too many points. More than using many points, the idea is to use many functions in the approximation basis and to have something that is robust to treat a lot of dimensions. This is the separation of variables, and something that selects the right function, and this is the sparse regularization.
Wonderful. Okay. Another question from
Can
John.
I have a follow-up on this one, Young-Soo?
Yeah, go ahead. I mean, but yeah, are you familiar with the SIND though?
Yes, exactly. This is the SIND, the Nathan Kutz. The only thing that we make is we put this in a tensor format because we are using, as you can see here, we are using this. Sorry, I arrive. We are using this in the separation of variable, but it's exactly the same. It's the same regularization, but we are taking to take this in different directions because we are making the separation of variables.
Great. But John, I guess that was your question, right?
Yes, the question about Cindy was my question, but I was wondering, how do you build a library of databases? You must have good physical knowledge to actually propose a library of function before you make the selection.
Exactly. One possibility is when we have not information, we take a very rich polynomial basis, or like in the SIND, we can put harmonic functions, exponential, all the things that you want. But from an industrial point of view, when we are applying this in industrial problems, and this is the advantage I arrive in my presentation, when we are treating this kind of problems, we have a lot of simulations. So this means that we have very nice candidates to put them in the basis. So this is one advantage, because finally we need to correct things that exist, because finally there are thousands of runs that exist, and this is the knowledge that exists in the industry. So we can improve, obviously, the choice of the basis. When we have not information, we take a basis that is rich enough, and the ANOVA is another choice that is very representative because we are looking for the functions that depends only in one of the parameters, and in order to compute, I come back, sorry, it's coming, this one. And when you are using the ANOVA, the advantage in the ANOVA is all the functions are orthogonal. And when you are considering all these functions, all these points, there is only one coordinate that is changing, all the others are constant. And now you can obtain a very nonlinear function in each one of these dimensions. And this means that all the things that are related to each one of the coordinates, not to the coupling, but to each coordinate independently of the others, you can obtain a very rich and extremely nonlinear function. And as soon as this is okay, now you add some green points, and with the green points, you are only trying to approximate all the correlations between the different dimensions. So we are using ANOVA for the function that depends only on one parameter, on one function, on one variable, and after we are using the green point that is a sparse sampling in order to obtain all the correlations between the different dimensions.
Thank you so much. Any other questions from the audience?
Yes, I have one. You don't have to read it. I can just ask it.
Okay, yeah, go ahead. I mean,
this is not a technical question necessarily, but if we still have time and no one else has a question, some people are still hesitating in embracing model order reduction, and sometimes they call it just, a smarter interpolation technique. They want to dismiss it this way. What do you reply to those people?
Yes, I think I agree with them. Is model order reduction? Yes, it's a reduced model, but we are not operating by projection and introducing this in the differential operator. This model order reduction at the beginning was this slide. We are using an approximation of my variable. We are in a reduced basis, obviously, because there are a number of terms. We put in the operator, in the differential operator, we project and we compute the solution. This is the classical model order reduction, like in the POD, like in the reduced basis, or like in the PGD. Now, this is okay. Now the idea is, and what is this? This is a smart interpolation. I like this. This is a meta model, a surrogate model, but you can also write this problem in this slide, the regressions, like this one, but in this case, L is the identity operator. There are no derivatives, but it's the same. I would like to approximate something that I know by something that has a separated representation. And in this case, we are making a PGD. There are no differential operators. This is an identity operator, and we are computing the different functions x, t, and p. So for me, the work is exactly the same. In one case, we could call it model order reduction because we are assuming a reduced approximation of a function, and we are trying to compute this function by making a projection, Galerkin or not Galerkin. And in this case, we could call it a smart interpolation or interpolation. I totally agree. But for me, this is also in this setting, but now the differential operator is the identity. But no problem for me. For me, we call it model order reduction if we are working in the weak or a strong form of a partial differential equation. And this, yes, this is meta modeling, this is model order reduction, this is interpolation. I'm not, everything is right. It's not an issue for me. But there's a confusion. I agree with you. There are many people that are assuming that this is meta modeling. Yes, this is meta modeling. But this is regression, and regression is machine learning. So machine learning, linear regression is a technique of machine learning. All these, yes, are regressions. And I'm not sure if this is model order reduction, this is machine learning, this is regression. I don't know.
Thank you so much for the answer.
Thank you very much. Thank you very much.
Thank you for the question too. Okay, any other questions? Well, if not, let's thank our speaker, the Paco, the Professor Chinesta.